Hello guys, let's prove that E is irrational. And I've given guys the hint to use the method of contradiction or proof by contradiction. So generally, for proving that some number is irrational, we have to use the proof by contradiction by stating that it is rational and putting in the ratio of some number by another number and having a contradicting statement. So let's see how we can prove E is irrational. Now, just before I rubbed it, the hint had contradict and an exclamation mark. So we need to use the expansion of E. So we know that E is equals to 1 plus 1 by 1 factorial plus 1 by 2 factorial plus 1 by 3 factorial and so on till infinity. So let's choose the opposite case we want for this proof. Let's consider, or let E be some number by some number. Let's say m by n, and we want m and n both belonging to integer value. We basically want them to be whole numbers, no fractional part or anything. So that means we have m by n is equals to this expansion right over here, or this series I shall say. So what I'm now going to do is I'm going to write few extra terms I think in the next step. So now what I'm going to do is first I'm going to multiply both left and right hand side by n factorial. So we have 1 plus 1 by 1 factorial plus 1 by 2 factorial plus 1 by n minus 1 factorial plus 1 by n factorial plus 1 by n plus 1 factorial plus so on into n factorial. So since this is an infinite series, of course there will be a certain point when 1 by n factorial and the preceding and succeeding numbers will come up. So n factorial by n factorial is just n into n minus 1 factorial. So you'll just have m n minus 1 factorial is equals to, now up to here, this n factorial will obviously be greater than 1, 2, 3 and so on until you have n factorial. So you'll have n factorial plus n factorial by 1 factorial plus blah blah blah. Here you'll have n factorial by n minus 1 factorial, which is just n plus 1 plus, now this is when it starts to get interesting, because right here you'll have n factorial by n plus 1 factorial. The next you have n factorial and plus 2 factorial and so on. So right here up to here we know that this is just integers, because n factorial will obviously be greater than the denominator and the factorial will simplify as n minus 2 n minus, or n minus 1 n minus 2 so on till we get that factorial, which will just cancel out, giving us just some integer values. Now what we have right here, this left hand side is also an integer, obviously, right? And up to here we also have some integer, and then we will have some fractional values. Now right here we cannot just say that, oh, we have integer equals to integer plus fraction, so proof by contradiction right away. No, because just because you have some fractional values doesn't necessarily mean that they will add up to not be an integer, because here 1 is just 1 by 2 plus 1 by 2, and what is 1 by 2? Well, it's just 0.5 plus 0.5. They are fractional values. We in fact have an integer equals to fractional value plus fractional value, but those fractional values add up to be an integer. So we have to prove further that these fractional values do not end up being an integer or whole number. Thus we would have an integer equals to an integer plus fractional values, and then we can contradict and prove is irrational. But how do we do that? So let's just focus on this sum over here. So let's call that sum to be s. And let's just simplify it over here. N factorial by n plus 1 factorial, well, this will just be 1 by n plus 1 plus, next will be 1 plus n plus 2, n plus 1, and the pattern will be like that, n plus 3 into n plus 2 into n plus 1, and so on. So we'll basically have some fractional values. And here we want this sum to in fact be altogether summed up to be a fractional value. And that will prove we will have an integer equals to an integer plus fractional value, which is just impossible. Hence, we'll get E is irrational. So, how can we prove that it is fractional? Well, we can't just end up with a number, can we? We have used general terms and over here. But you can see what we have right here is a series. So it is almost like a geometric series. It is some sort of series, and we know this series goes for infinite terms, and it would be great if we had a geometric series. To prove that it is fractional, we kind of need some upper bound and a lower bound. We want this sum to be greater than something and less than something. And we typically want it to be greater than 1 by some number plus 1 and lesser than some 1 by some number. Because here, if a number a lies between 2 and 1, a here will obviously be fractional, because it could either be 1.2 or 1.7 or anything or any number that is fractional between 1 and 2. We kind of want that sort of situation. And right here, we can already see that s will be greater than 1 by n plus 1. Because here we have 1 by n plus 1 plus some positive values, meaning this sum will be greater than 1 by n plus 1. Now, it would be so nice if we had s smaller than 1 by n. Thus, we would have s be an fractional value. I told you guys earlier this is almost a geometric series. Well, can we in fact make it a geometric series by replacing some inequality? And the answer is yes. So I'll write it over here again. 1 by n plus 1 plus 1 by n plus 2, n plus 1, and so on. So instead of n plus 2 into n plus 1, if we had n plus 1 into n plus 1, there'd just be n plus 1 square. And similarly, if we had n plus 1 cube, n plus 1 to the power 4, and so on, we would have a geometric series to the infinite terms that will converge to a value, because here the common ratio will be lesser than 1, because our n is just an integer and 1 by n will obviously be less than 1. So what I mean is, here we have the sum 1 by n plus 1 plus 1 by, I'll replace this n plus 2 with n plus 1, and what I will do is make this be n plus 1 square, and the next term will be n plus 1 whole cube. Now, will this sum be less than or greater than this new term over here, or this new series over here? Well, there's a quick kind of trick to it. If you replace the denominator with a lesser value, then this sum will now be lesser. Increase the value of the denominator, the sum will be greater, and the opposite for the numerator part. So we need to figure out what this sum over here is. So as infinity, well, our first term, let's call that a, is 1 by n plus 1, and the common ratio, as I said earlier, will also be 1 by n plus 1. So the sum of infinity term of a geometric series is a by 1 minus r, and let's just put the value in. You'll have 1 by n plus 1 by 1 minus 1 by n plus 1. So on the top you'll have 1 by n plus 1 by n plus 1 minus 1, which is just n whole divided by n plus 1, and right here we can cancel n plus 1 and n plus 1, and this will be equals to 1 by n. So we have proven what we wanted. Finally, s will be smaller than 1 by n. And as I talked earlier, we have finally found our upper and lower limit or upper bound, and therefore we have the sum, or the sum is greater than 1 by n plus 1 and less than 1 by n. So this right here proves that this sum over here must be fractional values. Because let's just take an example. Let's say you have 1 by 4 and you have x, let's say, and this is 1 by 3. So here obviously this must be a fractional value. And here we can prove that from over here we have an integer equals to an integer plus some fractional values. So fractional values, which is impossible. So this is impossible, and hence, since we had let E be rational and we contradicted that, so that means E must be irrational. So there we go. And if you learned something new, please like and subscribe.